When we're adding and subtracting rational expressions, we want to make sure that we have the same exact radical, same exact root. Basically, think of like terms. You need the same combination of variables and exponents, and these examples will need the same combinations as well of radicals and roots. So, for example, in this first one, I'm going to throw a 1 in front of this. I can always add a 1 coefficient. Notice that I've got 1 times the 4th root of 10, whatever that's equal to, and then 7 times the 4th root of 10. Well, we can consider them like terms because they have the same exact radical on each one, the 4th root of 10. So if I've got 1 of them in this hand and 7 of them in this hand, then altogether I have 8 and then 4th root of 10. When you're adding, just like with adding like terms, we're not going to change the radical part, we're changing just the coefficient, the number in front. Think of it like 1x plus 7x. If you add those together, you'll end up with 8 x's. That variable part at the end doesn't change, just the coefficient changes. That's all we're doing for adding and subtracting. Our next example has 2 and then times 8 raised to the 1/5 plus 10 times 8 raised to the 1/5. So notice again they have the same, think of it sort of as your variable. They have the same piece at the end there, so adding up like terms, if I have 2 of them and then I add 10 of them to that, I've got 12 total. That piece though at the end that's in common will not change. It's still 8 raised to the 1/5 power, but now I have 12 of them in front. And so for our last example on this screen, we come to one where we don't have the same number inside the radical. Well, the big common mistake that lots of people want to make with this is they just want to say, okay, well that's going to be the cube root of 54 minus 2 is 52. That's so wrong. That's very, very, very wrong. Don't ever, ever, ever do that. You can't subtract two things if they do not have the same number inside the radical in this case. So what we'll need to do instead is let's try to make the numbers inside the same. And so what we'll do, as you saw in the previous video, let's go ahead and try to simplify this cube root of 54 by doing a factor tree. So if I do that, I can break 54 down into 9 and 6, or whatever numbers you want to use that multiply to 54. I keep breaking this down till I get prime numbers. So 9 breaks down to 3 and 3, 6 breaks down to 3 and 2. In this case, we're looking for sets of 3 to be able to get out of this prison. So there's a set of 3 numbers that I have. That's going to come out front. So I have 3 times the cube root of, and then anything left over in your primes remains inside, so cube root of 2. We'll take a look at what's happened. I'm going to throw a 1 in front over here too. Take a look at what's happened. Now that I've simplified it, now I do have the same exact radical at the end, the cube root of 2, and then the cube root of 2. It's like they planned it that way. So now it's just like a problem up top. I have 3 of them, and I take 1 of them away, meaning when I finally simplify, I have 2 of them left over. That piece that's the same will remain the same. I have 2 times the cube root of 2 as my simplified answer. We'll go ahead and do the same thing even when the problems get more complicated and they throw variables at us. We want to think of like terms. Like terms need to have the same exact combination of variables and exponents and radicals. As long as everything is exactly the same, we can just add or subtract coefficients. So again, our first 2 examples will be fairly easy when they give us the same pieces. Both of these have the square root of w, so in that case I can add the coefficients. 1/5 plus 3/5 is 4/5 as my new coefficient. The like term piece, the radical at the end, will remain the same. So my simplified answer for this first example is just 4/5 times the square root of w. Next up, once again, I have the same exact combination of variables and exponents, same radicals, same everything. All that's different is the coefficients. Both have x times y to the 1/4 power. In that case, I can just subtract coefficients. 3 minus 8 gets me -5. And once again, that piece at the end will not change. So -5 xy to the 1/4 power. As our last example, once again, like the previous slide, we do not have the same thing inside the radical, so we cannot do anything the way it is. Instead, let's go ahead and do a bunch of simplifying and see if we can make what's inside the same. So in this case, we're looking for sets of 3 because I'm working with cube roots again. So let's kind of split the problem and we'll do like part of this at a time. So in our first example, we have the cube root of 2z to the 5th. Well, that 2's already prime, so there's nothing I can factor into. That 2 is in that prison for life. Z to the 5th, however, remember we wrote these out in the other video, means there's 5 z's being multiplied in a row. So I'll multiply 5 z's. Looking at it that way, I can see, yeah, I do have a set of 3 z's, so they get to be taken out. So in front of this, I'm going to have 12, and then that set of z's that got out What's left over inside is the cube root of 2. That's not getting anywhere, getting out of jail. And then notice I had 2z's left over that did not make it out of jail, so minus 2z squared. Okay, that piece is simplified. Let's go ahead and try the other side of this and see if we can make both things inside the same. Once again, I have a cube root, so let's break down 54. As we did in the last video, I think it was in the last one, we had 54 as well. So I'll go through that kind of quickly. Hopefully we've got the hang of it. I want a set of 3 to break out of this prison because I've got a cube root. I do have a set of 3s. They're right there. So they're going to come out front. I guess I'll write on the side over here. Remember, it was subtracting, so I'll put a minus sign. I have the 3 that I can take out. Notice there was already a z in front, so I have a minus 3z. And then inside that radical, I've got the cube root of that single 2 was left over, so that stays. And then z squared just means z times z. I can see that I'm not going to be able to get a set of 3, so that would say stay z squared. Well, lo and behold, look at that. We've got the same exact thing inside the radical at this point. I've got the cube root of 2z squared and the cube root of 2z squared. Because those are identical, I'm allowed to add or subtract the coefficients, the numbers in front. This time I've got 12z minus 3z. Hey, look at that. They were nice enough to even give us like terms in front as well. 12z minus 3z leaves us with 9z as our coefficient. And then as always, when we're adding or subtracting, our radical stays the same. So 9z times the cube root of 2z squared. Wasn't that fun?